So we'll start this class the way we'll start most classes, with a quick look at our calendar. Again, you have this on the back of your syllabus, but you don't need to open to your syllabus right now. This is class number 2, and today we talk about average and instantaneous velocity. So just a couple of things before we jump into the calculus stuff. First of all, on each table, there's a green folder. So if you haven't done so already, put your name at the top of one of the rectangles on the folder. And then every time you come into class, you sign in with what time you got here. So if you got here at 10:30 or 10:40 or 10:20, you just write the time. And this will be the way we will take attendance in this class. Also, the folder is going to be the way that we pass homework back and forth. So any homework you have to show me, put it in the folder right now. I'll grade it over the weekend. I'll return it to you in the folder on Monday. Okay? I don't need the pretest, no. No, the textbook homework and then the written answers to those questions about yourself as a math student and about the New York Times article. So any homework you have, you put in the folder. I'll grade it and give it back to you Monday. I wanted to make sure that people know that there's always a grace period on the homework. I'll take late homework up to a week after it's actually due. I recognize that sometimes life gets in the way and you can't necessarily do homework every other day for this class. Right? So you can get full credit on homework up to a week after it's due, but you probably don't want to make that a habit. The idea is to stay with the class, to be with the material, which will allow you to get more out of the actual class time we have together. Okay, another thing I wanted to mention has to do with this Bluetooth that I'm wearing right now. So I record each of my classes, and if you know how to find the thing on YouTube, you can go back and watch the video of any of my prior classes. So the title of the video from last class is up here, and you're probably going to want to write that down because it's just about the only way to find this video on YouTube is to know the exact title. So here's what it says. It looks like 2012, but that's not what it says. It says 201, that's Calculus 1 here. Then it says 2014 September 03 was Wednesday's date. Notice there's a 0 in the date. It's always a 2-digit date. So if you search for exactly that phrase with no spaces, I will be the only thing that pops up. And after class today, if you change the 3 to a 5, you'll find the video that we're recording right now. And so just to be clear exactly what it is that you would be watching if you watch one of these videos, we'll play a few seconds here. So as you can see, you'll have audio of anything I say, and you'll have a video of anything that happens on the smartboard. Anything that got projected up there, you will see in this video. Unfortunately, the mic doesn't pick up any of the wonderful questions that you will ask this semester, but this is the best that I can do. So if you wanted to review something that you saw in class but then don't quite remember while you're doing homework, you can check it out. If you miss class, you can check it out. But anyway, this will always be here. Another way to get to the videos is to go through Moodle. If you happen to log in, you'll find a playlist and it will get filled in with all the videos for the semester. Any questions on this? Okay, so jumping back here to the big packet, like I said, we're starting on page 11. One last announcement. Go ahead and grab one of these lime green bookmarks. This tells you exactly when the math studio right across the hall is covered by a math faculty member, right? You're welcome to go there anytime the building is open, but if you want to make sure that you're there when some math faculty member is on duty to take your questions, you can go during any of these times, right? Doesn't just have to be me. I'm not here very often. Sandy is here many more hours than I am, but go to any of these folks. They should be able to help you. All right, so at the top of page 11, we'll start with our daily summary, and we'll jump to Isaac. Isaac, could you read the daily summary for us? Thank you. And we'll go around to Ryan for number 1. Small. Thank you. So here's our calendar again, and right here in this column, it tells you when the projects are assigned. So I gave you two projects, and you might not have even opened them yet, but one of them is about arbitration, and the other one is about trucks. And they were both assigned starting last class, and then you can see in this next column, it tells you when they're due. So the arbitration project is due September 24, and then the trucks project is due the very next class, September 26. So about 3 weeks time between when the projects are assigned and when they're due. And the 3 weeks time should be an indication to you of how much time it's going to take to work through these projects. This isn't something where you want to try to do it the day before it's due. Bad things will happen if you try that. And we give you 3 weeks because they are intense, they are involved, and you really need some time to process these ideas. So Ryan just read to us that you are more than welcome to work with each other. You are encouraged to work with each other on these projects. Of course, you want to hand in your own individual work that you can say is yours, but certainly working with your neighbors is a great way to work through these projects, right? So if we take a quick look at the truck project, so again, if you have these two handy, we'll just look at them briefly. The very first page of both projects looks the same. It's some general info about projects. But inside the first page, the back of the first page, one of them says Project 2, and this one's about trucks. And at the top, again, it says you should work with other folks just so long as you credit them. But I want to start by looking at this table. This table gives you a suggested timeline for getting you through this project. To be clear, the truck project is not due until September 26th. So you can completely ignore our recommendations for how you progress on this project. It's due September 26th, however you get there. But the recommendation is that by class number 3, which is Monday, you will have answered question number 1 in the project. Where's question number 1? It's right on the next page in the middle. Right there is question number 1, right? And so you'll have to do some reading to figure out what's going on with all these numbers in the table, but try to get question 1 done by Monday. And then you can continue to just follow this timeline by class number 4, hopefully working and continuing to get a couple of questions, a couple of exercises done. What does class 4 mean? Well, this is on your syllabus. There's class 4 right there. And so again, it's just a recommended timeline. But if you follow the timeline, then you should be in a good position to answer the tougher questions which come late in the project. Any questions about this suggested schedule here? Okay, so this project is about trucks, and in particular, it has to do with what speed you should recommend to your truck drivers in order to minimize how much it costs you to pay them and the gas. Kind of these two conflicting things here. If you drive really, really fast, what happens to your gas bill? It's going to go up. But what happens to the amount of time you have to pay your drivers to be on the road? It goes down. And so we've got these kind of conflicting forces, similar to the New York Times article, where you're trying to like trudge through the snow or walk in the clear part. You got to try to find the balancing point. It's this tug. So the truck project, I think, will push you a little bit, but should be relatively straightforward. There's some linear regression. You might need to review how to do that. And the calculus is fairly straightforward once you know what you're doing through the material that we learned together. But then project number 1, which has to do with arbitration, is going to push you an awful lot. Project number 1 is way more involved, way tougher than project number 2. And the thing that makes it tougher isn't the calculus. In fact, the calculus in Project 1 is far easier than in Project 2. But it's all the reading that you're going to have to do to get familiar with these ideas that I'm assuming most or all of you have never seen or thought about before. It has to do with, let's suppose that as a class, and this will be an example that you read about, but as a class, we're going to take a week-long trip just to vacation in the middle of the semester. And we're either going to go to the mountains or we're going to go to the beach. Mountains or the beach. And what we have to do is decide as a group, we're only doing one of those things. Now, probably some of you want to go to the mountains and some of you would prefer to go to the beach, and we got to come up with some fair way to decide what to do. And that's what this project is about, is coming up with some fair way to pick between a number of alternatives. The difficulty is that there's going to be a lot of vocabulary you're going to need to learn about. There's some new notation. I should be clear about this too. There's a bunch of blank pages, blank looking pages in this document, and then eventually you get down to the reading. So right there is the reading. It says page 7 at the bottom of this page. It's not actually the 7th page in the project, but it was photocopied and it was page 7 in the book I got it from. And so a bunch of your time in this project is going to be about reading through this paper. And as you know, reading math is not the same as reading like science fiction, right? It's really a slow process where you got to make sure you understand the previous sentence before you move on to the next. So you're going to read all about this arbitration business, and you're going to get to this new notation here, and you're going to struggle a little bit with u sub e of b equals 6, and what does that mean? And you're going to take your time. But again, I really strongly encourage you to follow that project timeline that's on the back of the first page. Because like I said before, waiting until the day before this is due is just a bad idea. So anyway, here's the suggested timeline. In the middle column, it tells you what the reading assignment is, pages 7 through 9. And then the last column is the exercise, exercise 1. So unless you are a real go-getter between last class and this class, you guys are in theory like a little bit behind my schedule, but I didn't tell you about the schedule until now. You can catch up this weekend, I'm sure. So this is really spaced out. I try to be thoughtful in terms of spacing out the reading and spacing out the exercises. Notice that the beginning part, there's a lot more reading and not a lot of exercises, whereas at the end, there's a lot of exercises. So you want to put yourself in a good position to handle all those tougher exercises at the end when we've got the tools, the calculus tools to answer them. Okay, so I'm not trying to be intimidating here. I'm just trying to be realistic and give you a sense of what you have in store for you. Caitlin, who's the other person that's teaching this class with me, and I are very excited about these projects. This is the first semester we are using these 6 projects, and we think it's going to really contribute to the course, contribute to your learning experience. But it's a significant part of the course, and I just want to make clear that we're expecting you to spend a bunch of time thinking about these ideas. Any questions? Okay, thanks for bearing with me through that. All right, let us jump back to page 11. And here in number 4, it says we're actually going to jump a little bit again. So what we're going to do is jump to the group activities, which is on page 12. And you're going to see how far you can get answering questions on pages 12 and 13. I guess all the questions are on page 13. But go ahead and start reading on page 12 with your neighbors. If you get stuck, ask a neighbor. If all your neighbors are stuck, raise a flag. And then we're going to come back together at some point soon. Okay, so the 4 groups are in 4 different places, but I think everybody's gotten to at least the place where I was hoping we would get, and that's to grapple with that tough question 7 about the instantaneous velocity at a point. Let's actually have one group share their technique. Let's go to this table here. Haley, can you talk to us about what you guys decided to do for 7? So like 2.5 to 3.5? Mm-hmm. And then, so what did you calculate for those 2 points? So you found the distance and then divided it by the time, which is just an hour in this case. Yeah, and so that is an average velocity, but it's probably going to give us a pretty good idea as to what Hertz was doing exactly at that moment. He didn't really change things too dramatically in between that those 2 endpoints. So that seems like a good strategy to approximate the instantaneous velocity. Okay, so wherever you were in that project, go back a page. We're jumping back to page 11. There's going to be more jumping around today than normal. And we're going to try to tackle number 1 as a group. Who's our next reader over here? Ryan, you read. Brendan? Number 1 in the demo. Okay, so there's a formula which have we seen this in physics? I know it's only the second day of physics. Raise your hand if you're in physics. Just about everybody. So there's a physics formula for us, and we're going to use this formula to answer this question. So we need to plug in the specific values of A and V sub 0 and S sub 0. What does A stand for? Initial velocity is the V sub 0. Acceleration is what the A is. And we are in meters in this case. Does anybody happen to know what A is here on Earth? 9.8. So we're going to plug that guy in. A equals 9.8 meters per second per second. That's here on Earth. It's a different A on the moon. And so we can plug that thing in. So we go 1/2 of 9.8 times t squared. T is just going to be the variable for us. Plus, next constant is V sub 0. The 0 stands for initial. The V stands for velocity. There's one word in this problem that tells us what the initial velocity is. Dropped. So what does that mean for V sub 0? It's 0. It starts out at 0 meters per second. We dropped it. So we can plug that into our formula. 0 times t plus, and then finally we need the S sub 0. Now S, remember, stands for height. I don't know why we use S, but it's the standard physics letter for height or position. The initial position of this thing is how far off the ground? 450. So that's someplace right here. S sub 0 is 450. Defining 0 to be the ground. Okay, so we'll just clean this up and get the formula we're going to use for this problem. Half of 9.8 is 4.9. T squared plus 450. Now, what do we expect to happen to this ball when we drop it? It's going to go down. It's true. If you plug in t equals 1, what do you get? You get 454.9. It's going up. What's wrong? There? Yeah, that's what's wrong. The acceleration due to gravity, negative 9.8, negative 9.8, negative 4.9. That's just how we chose it. I mean, 9.8 positive is fine as long as you say positive is up. As long as you say falling is up, and that's probably not what we want to do. So down is negative. It's just a convention we agree on. So there's our formula. And here's what we're going to do. We're trying to find the instantaneous velocity at t equals 5. I don't know how to do that just yet, but I can find any average velocities I want. That's easy. So how about we look at the interval from, say, t equals 5 to t equals 7. I'm just going to pick an interval that contains the number 5. 7 is just a number I made up that's not too far from 5. And so this is the same strategy that Haley in that table shared with us. It's like, let's just find an average time interval that includes the number we're actually interested in. So what we need to do is find the average velocity. And we know that the average velocity is change in distance over change in time. We've seen that delta symbol before. Greek delta usually stands for change. In order to find the change in distance, I need to do some calculating. I need to figure out how high the ball is after 5 seconds, and then how high the ball is after 7 seconds, right? Well, we got to figure these numbers out, but we're going to call them S of 5 and S of 7. And in order to get the change in distance, the change in height, what do I need to do with these two heights once I found them? I need to subtract them. So there's my change in distance, divided by the change in time. How much time elapsed in this interval? 2 seconds. I'm just going to write 7 minus 5. so that we can really see there's a pattern here. That's what the formula is going to look like for us every time we do average velocity. S of something minus S of something, and then the bottom is the same, but no S's, just the times. Okay, folks with calculators, help us out. Somebody do S of 7. That is, plug 7 in for the T, but not everybody do that one. Somebody do 5. And then we'll get our two numbers up here. 209.9. If anybody confirms that, that would be great. Confirmed. Anybody have the 5 for us? 327.5. Super. Does that jive with what we expect the ball to be doing? Right, after 5 seconds, it's higher than after 7 seconds, so that's good. Downstairs, I have a 7 minus 5. And so if somebody wouldn't mind subtracting these numbers and then dividing by 2, we'll just get our final answer up here. Negative 58.8. Anybody else confirm that? Great. Negative 58.8. Let's get some units up here. What were the units for S up on top? Those are meters. And the units for time on the bottom? Seconds. So this must be a meters per second number. So negative 58.8 meters per second was the average velocity for that little interval from 5 to 7 seconds. What does the negative mean? It's falling. It's going 58.8 meters per second down towards the center of the Earth. Okay, so that's fine, but we want the instantaneous velocity, not just this average velocity. So how about we pick a different interval? We're still going to go from t equals 5, but what would we like to do with that other number? It was 7. What kind of a number might I do that would be better? Something really close to 5, like 6, or closer to 5, like 5.1. If you can find an average velocity over this little tiny tenth of a second, and it's going to be pretty darn close to what the instantaneous velocity was. So we're not going to write all the calculations again, but I would ask you to write this part for me here. Fill in the blanks on top, and then put those same two numbers downstairs as well. And then if we can get somebody with a calculator to do this one. So what goes in the blanks here? 5.1 minus 5, and then the same two numbers down here. Apologies, sometimes my S's look a little bit like 5s. So we'll get somebody to do, maybe 2 people can do that calculation, and then the rest of us or somebody else can do this one. Let's be really greedy here, 5.001. Thousandth of a second. Instantaneous velocities are hard to find. Average velocities are easy, even if it's a tiny thousandth of a second time period. So this one will get somebody with a calculator to type all this stuff in. And then we're just going to write down some final answers. So anybody who's not actively calculating for us, any questions on the setup here? Do we see that these average velocities are getting us closer and closer to the true instantaneous velocity at t equals 5? That's reasonable. Okay, anybody have numbers for us? 39.49. Good. Anybody have one for the bottom one? Okay, but while we're waiting for calculator folks to get the bottom one, I'll pull up a picture. So the equation of this parabola is kind of tiny, but it's down here in black. It's negative 4.9 x squared plus 450, which is exactly the equation for the height that we were looking at. And you can sort of almost see the ball falling down as you run along to the right on this graph. Just to be clear, it looks like if you follow the graph, the ball is getting further and further from this building. That's not what this is saying. Moving to the right on this graph is allowing time to elapse. The ball is just moving straight down. Right? Time is passing, and so Otherwise, the graph would just look like something going straight down. Okay, so we've got my fixed point up here. At 5 seconds, we're at 327.5. Wait, is that the number we wrote before? Okay. And after, let's see, so right now the other side of the ball, or the other dot that I have here is this thing at 9.55 seconds. I'm going to move that right now. And we'll move this point right here, and I'm just looking at these green numbers trying to get to 7 because that was the first calculation that we did. So something like there, that's close enough. And so when we subtracted the distances and then divided by the 2 seconds, we got whatever, what did we get? Negative 58.8, this is pretty close. I'm not exactly at 7, which is why it's a little bit different. But what did we really find? Like when we did this calculation, this thing minus this over this minus this, what are we finding with respect to that line right there? That's a slope, isn't it? Change in y over change in x, we're finding a slope. And in fact, you can see it here, the very first thing we wrote, change in y over change in x. It's just different letters. So what that means is that the average velocity is really just a slope of that line. And then I'm going to take this varying point, I'm going to move it to try to get this guy close to 5.1, which I think was the next number we did. Something around there that's pretty close to 5.1. This line right here is still a line that hits 2 points on the curve. It happens the 2 points are really close to each other, but it's just a line connecting 2 points. And what was our answer for that one? 49.5. So that's close. Again, I'm not exactly on 5.1. And then you can keep going, and eventually we get this line that's like basically 2 points that are pretty much on top of each other. They're still different. It's 5.0027, it's not 5, and there's still a line connecting 2 points on the curve, and I get that. I don't know if anybody had a chance to finish that calculation for us. Anybody have that bottom number?
I got negative
49.0049. And all of these numbers, this list of numbers, negative 58, negative 49.5, negative 49.005, are getting us closer and closer to the right answer. And at some point, we just have to guess until we have more tools. And what's our guess for the actual answer? That's really close to negative 49. So it feels like maybe the true answer, if we could do this forever, would be negative 49. Okay. Yeah, and so that word limit is definitely going to be important to us real soon. Yeah. All right, so quick definition. This is number 3 now. A secant line is a line that goes through how many points? 2. This is our definition. Maybe you've seen that word before, maybe not. But if you are connecting 2 points on a curve, then you are drawing a secant line. And so that line right there, even though the 2 points are just about on top of each other, they really are different points. And if we zoomed in, we'd be able to pull them apart a little bit more. And so that is a secant line. But that is really close to being a line that just barely touches the curve once. Technically, it hits twice, but it's really close to this magical line that hits the curve only once. And I know some people already know the name of that line. It's called the tangent line. That's a tangent line. So we're going to fill that in. Turns out that's a pretty poor definition. I'm just owning it right now. A tangent line is a line that goes through 1 point on a curve. And I say it's a poor definition because, for example, if you had that curve right there and you wanted to draw a line that hits it only 1 time, okay, there. That's not a tangent line. That's not what we mean by the tangent line. Right? At that point, the tangent line is something like that. There could be many other lines that hit it just at the one spot. So it's the only definition we have now. We'll fix it soon enough. And then we'll just come down here and conclude. So the graphical interpretation of average velocity. So Brendan shared with us that what we were really finding was slope. And if it's an average velocity, then we had 2 points that we were connecting. And what's the line that connects 2 points? The secant line. So slope of the secant line. That's what the average velocity is. But the instantaneous velocity, well, I mean, it sure feels like it's the same number, it's the same slope, but we really want that ideal line that just hits the curve the 1 time and then runs away. That's the slope of the tangent line. Okay, so here's what you're going to do. You're going to skip past the zombie thing. It's okay if you didn't quite finish it. I think everybody got far enough. We're jumping to page 14. Jump to page 14. And what you're going to do is continue this activity. I interrupted you before, but you're going to continue on page 14 until I say stop. So just go through page 14 as far as you can until I call us all back together with about 6 or 7 minutes left in class. So this is a continuation of the group activity. Go ahead. So I think all the groups are at least have thought a little bit about this H business. It just sort of comes in from out of nowhere. And let's be clear about what this H means. So the formula down there involved 5 plus H. So if I know that 5 is this spot where the fixed point is, and then plus H is just adding some number, then you know, like I could maybe say that this is our 5 plus H, that one that's going to move. And so that means that H is just this horizontal distance between the fixed point that we're interested in and then the varying point that's going to move closer and closer to the fixed point, right? It's just an alternative way to think about exactly the same thing. So the calculations look a tiny bit different because instead of going from 5 to T, generic, we're going to go from 5 to 5 plus H, different generic. And then on the next page, I know not everybody's had a chance to look through these calculations, but just the highlights here so we can do this last example together. S of 5 plus H, that's the height at the end. And then we subtract S of 5, that's the height at the beginning. And then we divide by, I mean, we've seen this pattern before, right? Where it's the same numbers, just without the S. Change in distance over change in time just looks a little bit different. So in this case, you got to go through some calculations, which I'll let you read later on. We're going to do an example like this in a moment. But eventually you end up with another formula that you could use. Instead of the one with the T's, you could use this one. They both give you exactly the same answers. Turns out we're going to use the H version far more, which is why I'm trying to introduce it here. But let's jump down here to the demo again. So we're going to finish up class with another demo. So important, the instantaneous velocity of the function y equals f of t at t equals a. I know there's a lot of letters floating around here. How much was a for the ball dropping problem? It was 5. 5 was the moment we were interested in. And so it looks a little bit more familiar if these guys become 5s, right? It wasn't f in the other formula, it was s, but it's just any old function. And so we just go find the change in height divided by the change in time. Do we buy that there's just an h down here? Because that's what you get when you do the a plus h minus a. Subtract them and the a's cancel. Okay, so that right there is our definition for instantaneous velocity. And then this fraction, that whole thing right there by itself is called the difference quotient. What's missing in that is in the instantaneous velocity formula? What is this limit stuff? So this we will talk about in detail next class. Andy talked about it, mentioned it today. But really we want to get accurate estimates. And the most accurate thing we could do would be to send h to 0 so that the fixed point stays and the varying point just kind of squeezes in until it basically lands right on top of the point that we're interested in. So number 2 says when we talk about slope of a curve, it's kind of a strange phrase because the only things that have slopes are what? Straight lines, right? You spent a lot of time in a lot of math classes talking about slope of a line. All of a sudden now we're talking about slope of a curve. What we really mean is the slope of the tangent line at that one particular point, right? We've got tangent lines that we can think about. So no matter how curvy it is, there's still a tangent line at every point. And we'll see them graphically in a couple of classes, but slope of a curve really references a tangent line. All right, moving on to number 3. So here's our last example. We're going to try to fly through this, and if I apologize, it's going to be a little quicker than I intended, but there is this video that you can check out later if you miss any of the details. Suppose Ian throws a grapefruit straight up with an initial velocity of 100 feet per second from a height of 6 feet. Without a calculator, let's find the velocity of the grapefruit 1 second into its flight. The reason this is tough is that I'm taking the calculator away. So you're not going to be able to do all of these estimates of average velocities over smaller and smaller time periods, because you don't want to be plugging in 1.001 seconds by hand into any of these formulas. So let's start with our S of t formula. So it's a 1/2. Its acceleration. In the earlier problem, it was negative 9.8. This problem is about feet. So we need to use the feet version of acceleration. It's negative 32. That's times t squared plus initial velocity. In the other problem, the ball was dropped, so there was a 0 initial velocity. But here, I'm giving the ball an initial velocity of 100 feet per second. Throwing it up, it's positive. And that initial velocity gets multiplied by t, plus S sub 0 is the initial height. I'm throwing it from a height of about 6 feet, plus 6. So crunching all this stuff together, just negative 16 t squared plus 50t plus 6. Okay, so here's our definition for the instantaneous velocity is S of, so it was a plus h on the previous page. The moment that we're interested in is 1 second in, 1 plus h. Fixed point at 1, just go over a little bit to this thing called h, then subtract the height at the fixed point, and then we divide by, you could put 1 plus h minus 1, but what is that? That's really just h, and it's always just h, because the a's cancel every time. So here's where things get a little bit tricky, and unfortunately we have 37 seconds to talk about how tricky this is. But S of 1 plus h, here's your formula in black for S. When I say find S of 1 plus h, you're replacing the t with 1 plus h. So both of these t's over here become 1 plus h's. So negative 16 times something squared plus 50 times something plus 6. Those somethings are both 1 plus h. 1 plus h. So I will underline to show you what's the same. This thing right here is S of 1 plus h. Also on top, I need to find S of 1. That's a whole lot easier to do. Minus, if we plug 1 in here, negative 16 plus 50 plus 6, I think it's 40. This right here is S of 1, if I did it right. And then it's still divided by what? H. Okay, so we are past time, so I'm going to give you a tiny bit left to do on this one. You got to do some algebra here. The 1 plus h squared, you got to FOIL that out. Then you got to multiply everything by negative 16. Distribute the 50. Lots of stuff is going to cancel. And everything left out on top, you're going to be able to factor h out of. Whatever's left on top, every single term is going to have an h, which you can pull out. And then finally, once you've pulled that h out, you're free to cross those h's off. And then at the end, plug in a limit as h goes to 0. I'm going to continue this video right now. You guys can go, but I'm just going to show the details so that if you have a chance to check out the video later, you can see them. Try it on your own, but if you want some assistance, just check out the rest of this video, okay? Have a great weekend. Okay, so next step in this problem, like we said, is to FOIL and distribute. So let's give it a shot. Negative 16 on the outside. 1 plus 2h plus h squared. When you FOIL that 1 plus h squared, and distribute the 50. I'm going to keep that 6 as it is. You're welcome to combine the 6 and the 40, but I'm going to leave it for just a second. That's all divided by h. Then distribute the negative 16. And then we'll copy everything else. Again, some of these things combined, but I'm just going to leave them as they are. and still divided by h. And the reason I wanted to leave them as they are was so that we could see everything cancel. So there's a negative 16 plus 50 plus 6. Altogether, that gives me 40. And it happens to cancel perfectly with that minus 40. So let's go ahead and combine the like terms that are left over on the top. So we've got negative 32h plus 50h is a 16h. And then the only h squared term is minus 16h squared. Still divide by h. And like I said, if you do everything right, you'll be able to factor an h out of the top every time you do one of these. You could factor the 16 out as well, but my goal is to get rid of the h on the bottom, so I'm just going to factor h out. And at this moment, we can then cancel those h's, and we're left with a much simpler equation, 16 minus 16h. And the last step was to finally take this limit that I've got written up here at the top in green. Limit as h approaches 0 of this thing. So I'll write our final answer here. The instantaneous velocity is the limit as h approaches 0. That's always part of our definition for instantaneous velocity of this 16 minus 16h. And then finally, we get to do something that seems too good to be true, but basically we just plug h equals 0 in wherever we see an h. When we do that, we just get 16 minus nothing, which is 16. So 16 feet per second is our instantaneous velocity at t equals 1. Last thing to say about this, if it was so easy to just plug h equals 0 in, why didn't we do that in the beginning? And the answer is we couldn't. You don't get to plug in h equals 0 here because there's an h in the bottom, and that would mean we divide by 0. So the entire process that we're doing is for the sole purpose of getting rid of this lousy h that's in the bottom. And this moment right here where we cancel it is the happy moment in our problem. Okay, so Kevin finally decided to let me know I made a mistake, so let's fix it. So negative 32 plus 58 should have been 18h. This guy's an 18. This guy's an 18. And this guy right here is an 18. Okay, so now I realize finally that I've made a royal mess of this because Kevin and I have discovered another error, and this one is even more fundamental. So I took half of negative 32 and got negative 16, good for me. And then for some reason I decided taking half was such a good idea, I would do it again. And that 50 should not be 50, bad, bad, bad. That should still be 100. So I'm going to erase all this and then try again. Okay, so second time hopefully better than the first. This should still be 100, t plus 6. All right, the red formula we've got there for instantaneous velocity is correct as long as I include the limit business that I have up here. I probably should have put that right in front of the red, but I'll just leave it as it is and then start plugging in. So s of 1 plus h, all of the t's in this formula become 1 plus h's. So negative 16 times 1 plus h squared plus 100 times 1 plus h plus 6. And we'll underline again, all of this is the s of 1 plus h that we saw over there. And then we subtract 40, although it's not 40 anymore, is it? Let's see. So we're finding s of 1. So negative 16 plus 100 plus 6. I think that's 90. I have no confidence in my ability to do math anymore. Let's back up. Let's see here. So s of 1 is now this guy, 90. Okay, so the whole thing is still divided by h. Now it's time to do a bunch of algebra. So negative 16 outside, we're foiling the 1 plus h squared. I'm going to distribute that 100. Plus now I'm just going to go ahead and start combining terms here. So 6 minus 90 is minus 84. Still divide by h. Still distributing a negative 16 through. Copy everything else, divide by h. Now, anything without an h should cancel, so let's take a look. I've got 100 minus 84 is 16, minus 16 is 0. I'll say it again, everything without an h should cancel. Unfortunately, it did. So copying the top, we get negative 32h plus the 100h is a 68h minus 16h squared, and that's still divided by h. And now because everything upstairs has an h, we can factor h out. So we get 68 minus 16h. And now the moment we've been waiting for has been to cancel the h in the bottom. And so all we have left is 68 minus 16h. And so now I'm going to put in that limit, which I should have been writing the whole time, but I've been super lazy. So it was green before, we'll keep it green. Limit as h goes to 0 of the thing we just calculated, 68 minus 16h. I'll just underline here, this guy got copied over to here. And doing this limit calculation is actually pretty easy because all we're going to do is replace the h with 0. Right? That's what it says to do. It says send h to 0. Okay, we're going to make that h really, really close to 0. How close to 0? Well, we're just going to make it 0. So this is equal to 68 minus 16 times 0. It's literally just substituting h equals 0 in. And 68 minus nothing is 68. And 68 feet per second is mercifully the right answer. And so you might be asking why we couldn't just plug h equals 0 in from the beginning if that's all that we ended up doing at the end. Why go through all the algebra? Just plug h equals 0 into the beginning. And the reason we don't do that is because we can't. We can't let h equal 0 because then you divide by 0. So that h in the bottom is bad news. And so we do all of this stuff to try to make it so that we get rid of that silly h in the bottom. Still there, but then finally, this moment right here is when we're happy, which is what Pharrell was talking about in that song. It's the moment where you get to cross off the h in the denominator.